This video will look at making predictions using population models. So we could determine the likelihood of very specific results, given that we know something about the initial population that we're dealing with. So just something I'm keeping in mind, we are looking at populations here. And if I'm looking at population models, when I'm talking about averages, I'm using the parameter symbol mu. If I'm talking about standard deviations, I'm using the standard deviation sigma. These are called discrete random variables, the things that we're looking at today in particular. That means they're whole number values, discrete, and there are certain likelihoods for those situations. For example, suppose that Jessica's playing the video game Pokemon Sun. There's a 10% chance that she finds a rare creature in a given region that she's looking in this game. She will keep doing encounters until she either finds a rare creature or she'll give up after 4 encounters. Draw a tree for this scenario. Okay, so first set of branches, this represents the first encounter. And it's either the rare thing that she's looking for or it is not rare. The likelihood that it's this rare creature is 10%. So then that means there's a 90% chance that it's not rare. She would stop if she found it here. So one possible ending spot in my sample space, I could have R. If she doesn't find it, she would have another encounter where it's either rare or not rare. Still a 10% chance of finding that rare thing on the second pull. A 90% chance that she doesn't find it. If she finds it, she would stop after 1, 2 encounters. If she does not find it on her second try, she's going to try a third time, either finds it or does not find it. Stops if she finds it. She keeps going if she doesn't. Stops if she finds it for the rare. And at this point, I'm 1, 2, 3, 4 encounters in. I would also stop at this, even though she's not found what she's looking for. So in this situation, there are certain likelihoods of making each step along the way, and there are a whole number value of steps that we can take. It says let x represent the number of encounters. Calculate the probability that x equals 1, 2, 3, and so on. Okay, so I'm going to take this tree that we have, and I'm just going to label it by the number of steps to get to these ending spots. So this is 1 encounter. This is not an ending spot of the tree. I have to stop on the outsides of the tree. But this is 1, 2 encounters for this scenario. 1, 2, 3 for this. And 2 different ways of getting 4. Could end on the 4th one where she finds it, or she can end on the 4th one where she doesn't find it, but she's encountered 4 things at that point. And I want to find the probability of each of these events. So I'm going to make a little grid where I have my x values and their corresponding probabilities. Some of these are going to be easier than others. For example, to get x equals 1, that's only this probability of r, and that's a 10% chance. If I'm looking at 2, that's this not r and then r path. That's 0.9 times 0.1 or 0.099%. 3 is here, 0.9, 0.9, 0.1. A calculator that gives me 0.081. And finally, for 4, I can either calculate the probability of this plus the probability of that, or just a reminder, everything adds to 100%. So I can take where I'm at so far. I have 1 minus 0.1 minus 0.09 minus 0.081. This last category is 72 So here I have certain numbers of encounters, and I have their probabilities. This thing is called a discrete random variable. So looking at this, if I was trying to figure out, okay, well, what's the average number of encounters that she would get? It's probably going to take more than one encounter for her to find what she wants or stops, and probably more than even two, and possibly more than three. Because if you're looking at this, the bulk of the time, it takes her 4 encounters to run into a situation where she stops playing. So I don't know for sure what I'm expecting, but maybe this is 3 or 4-ish encounters. That's a guess. We're going to have to calculate and see if we can get something better than ish. At least that's a starting spot. Create a probability histogram. How would you describe this? Okay, so probability histogram. This is just a histogram, so it has the number of encounters, and I could have 1, 2, 3, or 4 down here for the number of encounters. And for probabilities, it looks like I have everything from 10 up to 72.9%. So I'm going to count by 20% or so. For 1, the probability is 10%. For 2, the probability is 9%. For 3, the probability is 8.1%. And for 4, it's 72.9. So if I'm looking at this graph here, and reminder, any good graph has a title, so make sure you put a title on this. A good title might be something like the likelihood of blank number of encounters playing Pokemon Go. If I wanted to describe this graph, I would say that this is unimodal. Looks like there's one mound to it. And it looks like there's a long tail coming off to the left side. So I would also describe this as being left skewed. Now I want to go about trying to find the average of this thing. This is going to be sort of the middle of my data set to some extent. And if you just look at the amount of weight here to the right, it's really unlikely that I have an average of 2.5, considering there are so many values up here at 4. So the one thing that I don't want to do to find the average, and the average I'm calling the expected value. So this is what I expect to have happen. It's the average for the population. And I'm going to do the wrong thing here first. It's not 1 plus 2 plus 3 plus 4 divided by 4 values. That's how I found my sample average before. If I do that here, this is going to give me a value of 2.5. But we saw looking at our graph that 2.5 was unreasonable. It should be a higher value there for the average. So let's try to fix this. And also let's see where things went wrong. So this is not the correct way to do this. So I'm just going to write no by this, so remember that we're not supposed to do it this way. But let's see what this is really doing. This is the same thing as saying 1, 2, 3, and 4 are all equally important. They show up 1/4 of the time. So the way that this is set up was 1 had a weight of 1/4, and 2 had a weight of 1/4. 3 had a weight of 1/4, and 4 had a weight of 1/4. So when I found this average here, I added my values together and I divided by 4. This said they were all equally likely. It is a weighted average. Now the problem here is when I look at my table, I see that 1, 2, 3, and 4 don't all show up the same amount of times. 4 shows up considerably more often at 72.9%, and 1 only shows up about 10%. So if I want to do this the right way, I need to fix my weights. So this will be the correct way of looking at finding the average for the situation and for a population in general. So my expected number of encounters. This is like an E with an extra bar. That stands for expected value. That's just another way of saying average. That's that symbol mu. I have 1. It doesn't show up a quarter of the time, though. 1 shows up 10% of the time. So I'm going to go through and I'm going to fix the weights, and I'm doing this instead of doing the division. 2 showed up 9% of the time. Next value in my list, 3, and this showed up 8.1% of the time. And I had 4. 4 showed up 72.9% of the time. So I am weighting them by their actual probabilities here instead of saying that they're all equally important, because they're not all equally important. The 4 is considerably more valuable here because it has such a huge weight. I'm going to type this into my calculator and I'll see what I get. Reminder, just looking at the graph, it kind of looked like it should be 3 or 4 or so. And when I do this, I get something like 3.439. And this is actually the exact value. I don't even need an approximate here. I have an rounded. So if Jessica plans to continue playing Pokemon Sun this way, where she does 4 encounters, either trying to find the things she's looking for or giving up, she should expect about 3.4 encounters on average with this process. So it's going to take her a long time to find what she's looking for, the rare creatures. So what I've done here to find this average is I've taken the first X value and I've multiplied that first X value by its probability. So I have the first X value times the first probability, the second X value times the second probability, and then I add them all up. Another way to write this, I have this symbol means add. I am adding all of the individual X values times their individual probabilities. This is just shorthand of saying the same thing we're doing here. We're multiplying X times the P's, and I'm adding them up. So I'm going to keep that in mind when I look at another scenario here. I'm going to eventually find an expected value. To find this expected value, I'm going to multiply my X values times the probabilities, and I'm going to add them. So here's a new scenario. And here's a scenario where we can actually figure out what the answer should be before we even type anything in our calculator. Mr. Worry plans on flipping a coin twice. Let X represent the number of heads. Calculate the probability of 0 heads, 1 head, and 2 heads. This is a random variable. When I flip a coin, I can get anywhere from 0 to 2 heads. And there are different outcome likelihoods for these outcomes. So first coin flip can be either heads or tails. And assuming this is a fair coin, let's say 50-50. Second can be either heads or tails, regardless of what really happened there on the first flip. Let's label this with the number of heads. So heads, heads, that's showing up twice there. This is X equals 2. Heads and then a tails, that has heads showing up once. Tails and then heads, that has heads showing up once. Tails and then tails, nothing but tails. There are 0 heads in that bottom sequence. And let's find the probabilities for these things. For heads, this is 50% times 50%, or 0.25. And actually looking at all of these, this is going to be 0.5 times 0.5. So this has a probability of 0.25, 0.5 times 0.5 again, and 0.5 times 0.5. I have 0.25 there as well. So taking this information and putting it into an easier to use little table here, when I flip a coin twice, I can have 0, 1, or 2 heads. The probability of getting 0 heads is 25%. The probability of getting 2 heads up here at the top, 25%. And the probability of getting 1 heads, adding these together, is 50%. So before I try to do the formula where I find the average, I just want to think about linguistically what's going on here. If someone told you how often should you expect to get heads, you might say 50% of the time, or 1 out of 2 flips. So for the expected value here, I'm expecting to get 1 out of 2 flips. Let's see if this shows up. My first x value in my table was 0. The probability of 0 is 0.25. Next x value in the table, I'm adding these up as I go, is 1. The probability of 1 is 0.5. Finally, I got 2. The probability of 2 is 0.25. I'm going to type this into a calculator. I have 0, I have 0.5, I have 0.5. I'm going to add these together, and I get 1. I'm counting the number of heads, so my average here is 1 heads. In writing out the sentence that would go along with this, I expect 1 heads on average when I flip a coin twice. So expected value, I expect, that's where that symbol in language comes from. Average, that's where the mu comes from. That's why those things are kind of interchangeable. They're both describing the same situation. So you can use either one of these sets of notation. You don't have to use both symbols. But I expect 1 head on average for every 2 flips of a coin. That sounds reasonable. Now, sometimes I will get less and sometimes I will get more. So the other component of this is looking at the spread. Let's do one more though. So I want to find the average. Calculate mu. That's the expected value. That's where I'm multiplying all these individual x values by their probabilities, and I'm adding them up. The Keno 3-spot game lists the probabilities of winning $2 at 1 in 8, $25 at 1 in 73, and let x represent the amount you win when you play the game. Okay. So I'm going to be a little bit careful about my language for winning and netting here. Winning, I'm thinking, is the money that I'm getting, not accounting for how much the game would cost. If I'm wondering what my net is, then I might factor in the cost. So for example, I might win $2 even though the game itself cost $1. So I'm up $1 even though I'm getting 2 back from them. Okay, so I win $2 1/8 of the time. There's a 12.5% chance of that. $25, not accounting for the cost of the game, just $25, is a 1 in 73 chance. I'm doing 1 in 73 in my calculator. And I get 0.0137 or so. This is an approximate. And if you're looking at this and thinking, that's not 100%, these are supposed to add up to 100%. That's because we're not accounting for a really important situation, the reason why Oregon Keno exists. 0. The majority of the time that you play the Keno, and these are the real odds of winning in payouts last time I checked for the Oregon Keno, 0 happens by far more often than any other category. You lose. So to figure out what percentage I need here, I'm going to take 100%. I'm going to subtract these two numbers. So I have 1 minus 0.125 minus 0.0137. 86.13% of the time, I lose. So if I'm looking at this game, I see that $25 and I'm thinking, I stand a chance at winning a considerable amount of money. Even getting the 2, I've doubled my money and I'm feeling pretty good about that. So I might be curious, what's the average amount that I would win if I played the game? Because on average, if I'm winning $3 and it only cost me $1, I might be pretty happy about that. So first X value is 2. The probability is 0.125. Plus the next value is 25. The probability is 0.0137. Next value is 0. 0 doesn't contribute a lot to the average, but I'm still including this. It's a good thing to get in the habit of doing. It doesn't contribute to the average, but it contributes considerably to the spread. And I get 0.593 or so, or 59.3 cents, because this right here is in dollars. So here's what this means. If I play Keno, I'm expecting to win 59 cents on average or so. The problem is the game cost $1. So the cost is less than the amount that I expect to win. And let's flip that. The cost is greater. It cost $1. I expect to win 59 cents. I am losing money on average. I want a situation where I'm expected to win more than I'm putting in. That's good for me. This, I'm making less money than what I started with. So should I play it? I would say not for investment purposes. It might still be fun to play the game, but I'm not going to intentionally do this thing with the hope that I'm going to make money. Sometimes I will, but often I won't. So why do people still play this if on average they're losing about 40 cents per game? Well, that's because they're chasing this 2 and this 25. There's a considerable amount of swing and variation when I'm looking at the odds and the payouts here. So it's not enough to just look at the average. I also want to know how much things vary from the center. So I'm going to calculate the variance here for this given situation. And I'm going to do it wrong first. This is the old way. This is how I did it if I was looking at a sample. It would be wrong for me to try to find the variance by taking the value 2 minus the center, squaring it, adding the next value minus the center all the way to the last value minus the center, squared, divided by the number of values minus 1. Because what I'm doing when I do this calculation here is this assumes that everything has an equal weight. So again, I need to fix the weights. We're getting a little bit deep in theory here today. I know that can get challenging. So if you have questions, please reach out to me so I can help you out with this. but also let's try a few out and just see if it starts to make more sense as we get some practice in. So I'm finding the variance first, and I'm going to do this the correct way. I like taking the value minus the center, but instead of dividing this and saying everything is equally likely, I'm going to multiply this by the probability of the event. So I'm going to multiply this by 0.125. I'm going to line these up vertically for this one because I find that it makes it easier to see. I'm going to take the next value in my table. Next value is 25. The average is still 0.593. I'm still going to square it, but the probability of 25 to keep things nice and balanced, the actual weight there is 0.0137. Finally, I have 0. And I want to say that 0 is really important because it shows up a considerable amount of the time. So I'm going to weight this by the probability of 0. That's 0.8613 or so. I'm going to type this into my calculator and I'll see what I get from my variance. As I do so, I'm just reminding you what I'm doing here. I'm taking the value minus the center. This is telling me how much it deviates from the center. And I am weighting it by their corresponding probabilities. A good casino game, good for the casino owners, will have a small average. They want to make money, but they'll have a large standard deviation and variance. That gives you the feeling of getting those highs and those lows while you're playing. For example, I might only expect to win 59 cents, but my variance is 8 or so. In order to get my standard deviation, I need to take the square root of the variance. Taking the square root of 8.711 gives me a standard deviation of approximately $2.95 or so. So the standard deviation describes the spread from the center. So if I was drawing out a graph, I'd probably want to start that graph at 59 cents or so, and I'd be counting by $2.95. So there's a ton of variation in this data set. So to find this, I took the first value minus the center, and I squared it. I square it so I don't get negative numbers anywhere in this process. For example, this would have been a negative number here. I multiply it by the probability, and I add them up. So another way to write this symbol means add. I am adding my individual values minus the average squared times their corresponding probabilities. If I want the standard deviation, I need to take the square root of the variance. We're going to do another one of these calculations, and we're going to use the average and the standard deviation in context so we can see how everything kind of ties together. What is the usual amount for someone to win playing Keno? This seems like an important game to know before you start. Important thing to know before you start playing the game. And as a reminder, what does usual mean? Well, usual means that I'm going to come from the average, and I'm going to go up and down 2 standard deviations. This tells me what should happen most of the time. So in this case, my average is 0.593 for Keno. That's how much I expect to win per game. And I have a massive amount of sway with the standard deviation of 2.95 or so. I'm going to type this in once with a minus and once with a plus. And let's see what we get. Now in practice, I'm not going to get a negative number here because it's not like I'm so bad at playing Keno that they ask me to give them more money than I've already paid. So even though I'm getting negative 0.5307, worst case scenario is still just winning $0. And for the high, changing a minus to a plus sign, I have $6.49 or so. So I should expect anywhere from losing all of my money to gaining $6.49 on average per play. There's a huge amount of spread when it's looking at what can happen here. So small average, massive spread. Let's see what's going on for the Pokemon example here and try to figure out how much spread or variation is anticipated for the number of encounters. So just relisting what we have so far, there's a 10% chance that she found the creature she was looking for on the first try, a 9% chance she finds it on the second, an 8.1% chance of finding it on the third, and a 72.9% chance that she either finds it on the fourth one or gives up. When we calculated the average, we got 3.439. So calculate the standard deviation. Before I do that, I'm going to calculate the variance first. The variance is my standard deviation squared, and I'm looking at a population, so I'm using the symbol sigma here. I'm going to take my first value in my list, 1. I'm going to subtract the center, mu. I'm going to square it, and I'm going to multiply this by the probability of 1, 10%. I'm going to take the next x value, subtract the center, squared, times the probability. And I'm going to add these up for all 4 of my initial values there. Let's take a look. 1 minus 3.439. Squaring it, I've taken the first value, I've subtracted the center, I'm squaring it so I don't get a negative, and I multiply it by the probability. Next value, I have 2 minus the average. The probability of 2 is 0.09. Plus, the next one's going to be 3 minus 3.439 squared times the probability, 0.081. And the last value here, I have 4 minus the 3.439 squared times the probability, 72.9%. I'm going to type this in. We'll see what we get. Once I have this, I will have both the average and the standard deviation, and I'll be able to describe what it means for something to be usual or unusual. And I'll be able to calculate z-scores if I wanted to calculate some z-scores. And we will calculate a z-score together. So I get 1.026 or so. So my standard deviation, which is the square root of my variance, is going to be the square root of 1.026, which is approximately 1.013 encounters. Would it be unusual to find the rare creature that she's looking for in the first attempt? What is the z-score for this event? Okay, so we're told that these creatures are rare. Let's see if it's really actually rare. Let's see if this is more than 2 standard deviations away. The z-score gives me the number of standard deviations from the center. And if I have a z-score between 2 and -2, I'm within 2 standard deviations, and that's the definition of what it means to be usual. To find a z-score, I take the value that I'm curious about, I subtract the average of the center. This gives me the total distance away, and I divide by the standard deviation to see how many times the standard deviation fits in that gap size. Let's fill in our numbers. Would it be unusual to find it in the first encounter? My value is 1. 1 compared to, I was expecting 3.439 encounters. So I'm off by like 2 encounters. That would be considerably lower than I was anticipating. The standard deviation is 1.013. Let's plug that in and see what we get when we put it all together. I get negative 2.41 or so. It would be unusual because it's more than 2 standard deviations away. If I'm drawing my picture, this is almost 2.5 tick marks away from the center. It would be unusual to get the rare creature on the first encounter. In fact, on average, I would expect it takes 3 encounters to either find this thing or to just kind of give up. So this process of finding these averages and standard deviations, this is just looking at sort of one situation at a time. But I'm wondering if we can take what we know about a single game and multiply this to look at 2 or even 3 games. So this is just getting me into the headspace of how can I combine scenarios. So let's consider the situation where I'm inventing a game and I can win the amounts of $0, $10, or $30 if I play this thing once. How much can you win if you play the game twice? How much can you win if you double the payouts? Okay, so let's look at these 2 very different situations. I'm going to start with doubling the payouts because I think that's easier. Instead of winning $0, I'm multiplying that by 2, so I would now win, oh, still 0. Okay. $10. I'm multiplying that by 2, so I would expect to win $20. $30, I'm multiplying that by 2, that's now 60. So if I wanted like a double-sized bet, I'm making everything twice as big. It's 0, 20, and 60 instead of 0, 10, and 30. Let's compare this to taking the amount that I win on the first game and adding the amount that I win on the second game. And we're going to list everything that can happen. Well, one thing that could happen, just doing a little bit of scratch work here up in the corner, is I could win 0 on the first and 0 on the second. 0 plus 0, this would give me a total of $0. So it's still possible that I lose. I could win $0 on the first game and $10 on the second game. I could get 10. Likewise, I can get 10 and 0. That also gives me 10. I could win 0 and 30. That gives me 30. I can win 10 and 10. That would give me 20. I could have 10 and 30. That would give me 40. Or I can have 30 and 30. That would give me 60. So it looks like I can win 0, 10, 20, 30, 40, all the way up to $60. Because when I'm combining these things, I don't have to win the same amount on the first game and the second game. It's almost like I have a safety net. It's possible that I lose on the first one, but I win on the second, and I'm still making a little bit of a profit. Here, I'm just making all of these things bigger, so more risk in general. Something that's a little bit odd and might be hard to wrap your head around first here is if you tell someone x plus x for random variables, this is not the same thing as 2x. And you're thinking, hold up, that goes against every algebra thing I've ever learned. Let's think about the subscripts. the amount that you win on the first game does not have to be the same as the amount that you win on the second game. So when you see x plus x, these things are not actually like terms. They could be different values. And because they have different subscripts, I can't combine these things. So there's a very huge difference between playing something twice and doubling your payouts there. So here's a tip for trying to figure out which one of these scenarios you're looking at. When writing out an algebraic statement to represent a scenario, keep in mind that each variable represents an event. And in particular, the number of variables is equal to the number of events that are going on. So let's look at some examples. A represents the cost of an adult meal at a restaurant. C represents the cost of a child's meal at a restaurant. Write out the statement that describes two adults eating meals. Okay, and they don't have to order the same thing. So I have two adults. I should see two letters showing up because I have two events. So I'll have the first adult's amount and I'll have the second adult's amount. B, one adult eats the same meal twice. They had it, they love it, they're just going all in. In this situation, there's only one person that we're looking at, so I'm only allowed to use the letter A for adult once here. Now, since it's the same meal twice, they're going to take whatever the cost was, if it used to be like $10, and they're going to double it now. So here's the difference between x plus x and 2x. X plus x represents two different individuals. 2x represents the same individual twice. Let's look at some more scenarios. One adult eats a meal and they tip $5. One adult, so I'm only allowed to use the letter A and once when I'm setting up the problem. They tipped $5, so plus $5 to their cost. One adult eats a meal and tips 15%. So if you're tipping 15%, you pay for 100% of the meal. That's how paying for meals work unless you have some sort of coupon or something. And then you're going to add a tip amount of 15%. So in total, you pay for 115% of the cost of the meal. One adult, so I'm only allowed to use the letter A once there. They tip 15%, so they're paying above 100, so they're starting at 100%, and they're going up 15% more than that, 1.15A. If you're having a hard time seeing that, I'm going to write this a little bit different here. You could break this up as the cost of the meal plus the cost of the tip. The amount for the meal is A, the whole cost. The amount that they tip is 15% of A. I have to be a little bit careful though, because this is the same meal that we're talking about. The tip is calculated on the same A. So these are actually like terms and you should combine them. So if you have 1A and you're adding 0.15A, this is the same thing as 1.15A. So it's not okay to write A plus 0.15A unless you really make sure that the reader knows you have the same subscript to show that this is really just happening for one individual. Let's look at another one. One adult and a child eat a meal. The child's meal is 25% off. They tip $20. Okay, if you're watching at home, pause the video, try this out, see if you can write out the letter combination for an adult and a child. Keep in mind that the number of variables is the number of events. The child's meal is 25% off, and they're tipping 20% on top of that. So again, pause the video, give it a try. Okay, assuming you paused the video, this is what I had. There's an adult, and there's the child. They're spending 100% of the adult's meal. The child's meal is 25% off, so that means that they end up paying 75% of the child's meal. 100 take away 25. They tip 20, so I am adding 20 to that amount. If I didn't like this, I could try to draw a tree, but these trees are going to get really long and really complicated. So we're going to see that these letter combinations will save us a little bit of time. Now, the neat part is assuming I know averages and standard deviations for both the adult and the child meals, I can find the averages and the variance for combination of events here. So when I'm doing the notes on this page, this is only use when you know the starting averages and standard deviations, and you want to look at combinations. I have the rules here. I'll talk about the rules here in a second, but we're just going to start with the average and try it out for each, because all of these rules on the side for expected value for average really work by plug in your averages as you would think that you should, and then you're done with the problem. So here's what I mean by that. 2 adults eat meals. So letter combination. I'm looking at A and A are those 2 adults. Now I want to know the average. So that for this entire column here, I'm going to be finding the average cost of each of those scenarios. If I just kind of thought this through, if the average cost of an adult meal is $15, then I expect that this first meal is going to be $15. If I expect the average cost of a meal is $15, then I expect the second meal to also cost $15. So if they're eating together and I'm getting the ticket there, I'm expecting to get $30 on average for the 2 of them. 1 adult eats the same meal twice. That was a letter combination 2 times A. I expect their meal to cost $15, and they're getting 2 of those meals. 2 times 15, again, gives me $30. It doesn't actually look like there's a difference between these. We'll come back and we'll see if the variance changes. 1 adult eats a meal and they tip $5. Adult and the $5 tip. It's $15 for the meal. It's $5 for the tip. I expect them to spend $20 on average. An adult eats the meal and tips 15%, so they're spending 115% of the cost of A. So it's 115% based off of the $15. At 1.15 times $15, this gives me $17.25. The behemoth one, the last one here. An adult and a child's meal is 25% off. They tip $20. Adult, 25% off the child, so that's 75% the cost of the child meal. And they tip $20. I expect the adult meal will be $15. So I'm plugging that in for A. 0.75. C. I expect the child meal will be $10. I plug in 10 for C. So all I'm doing this whole column when I'm calculating the average for letter combinations is I set up that letter combination and then I plug in the numbers. Variance rules are a little bit different. Two big things to keep in mind. These last two rules are just kind of an extension of the same fact, and that's variance only cares about things that vary, variables. For example, if I'm looking at the variation of A plus A, I'm going to take the variation for A, that's 3, and I'm going to add the variation of A, that's also 3, to get a total variation of 6 if I was looking at 2 adults eating a meal. I'm going to jump to C to show you the difference here when I have, instead of 2 letters showing up, a number like 5. So the variance of A plus 5. A varies. Some meals can cost more than others, and the amount they vary by is 3. $5. If you take your distribution and you move it 5 units over, it does not change the spread. You have the same spread here that you do if you added 5 to all of those values. So the variance notices the A, it's got a letter piece to it, but it ignores any numbers that are by themselves not linked to variables because they're constants, they don't vary. So this would be the variation of A plus that number 5 does not vary at all. I have 3 plus 0. This gives me a variation of 3. We're going to look at another example of this down when we're doing E, but just as a note, the variance only cares about variables. If there's a number, we can cross out that constant that's being added. It only combines different values. Okay, last variance rules. If you go back to the long formulas here, when we were finding the variance, we were taking the value minus the center and squaring it. So if you have the variance of something like 2x, this 2 is going inside those parentheses and it would end up getting squared. So any number on the inside, when it comes outside of the variance, you square that value. Let me show you what that looks like. One adult eats the same meal twice, and I want to know what the spread looks like. So I'm looking at the variance of the same meal twice, 2a. This number is not on its own. It's linked to a letter, so it is linked to a variable, so I do care about it. When I'm pulling a number outside of the variance, I square that number. 2 squared is 4. The variation for A, looking up top, was 3. 4 times 3 would give me a variation of 12. Let's see another one of those rules. Variation, we're looking at the 15% tip one here. 1.15 times the A. This is linked to a variable, so I do care about this 1.15. When I take this 1.15 and I pull it out of the variance, it becomes 1.15 squared times my old variance. My variance was 3, still 3. I'm multiplying this by 1.15 squared, and this gives me something like 3.9675. Let's look at the behemoth example where we bring all these rules together. A plus 0.75, C plus 20, and I'm looking at the variance. First thing I'm going to do is notice that I only care about variables. A has a variable, so I do care about the variation of A. 0.75C, that has a letter to it, so I care about that 0.75C. 20, that doesn't have a letter linked to it. It will not contribute to the spread. I can ignore the 20. The variation of A, I know that number, that's 3. So I have 3 plus, I'm looking at the variance of 0.75C. There's a number inside of the variance next to a letter. I want to bring this thing out. When I pull this number out, I have to make sure that I square it. So I have 3 plus 0.75 squared times the variance of a child's meal. I'm going back up to the top. Variance of a child meal was 4. I'm going to type this into my calculator. And I end up getting 5.25. So 2 different things kind of came up in this lesson. One, if I have a grid where I have a whole bunch of probabilities and x values, I have processes for finding both averages and standard deviations. If I'm given averages and standard deviations, I have a whole bunch of rules for combining those things, so I don't have to go back to really, really long formulas. This last page is just a whole bunch of shortcuts that's going to save me time in the long run. This will take a while to get used to. There's a lot of symbology going on with these problems, but this is just a stepping stone to get us to our big goal for statistics, which is to be able to make predictions about a population based off of a sample.